Alright, so before we start talking about advanced static analysis and dynamic analysis, let's do a recap on basic static analysis, or what we have covered up until this moment. So we covered basic static analysis. We covered what are the things, or what are the items that we look to collect when upon handling or analyzing an executable file or just a binary. Basically, we look to extract strings, we analyze the portable executable header. This is especially true when handling or analyzing Windows executable files. Indicators of compromise, IP addresses, hashes, DNS names. This is especially connected to strings. You may find these items when extracting strings. Architecture and header, whether the file is 32-bit or 64-bit, and header information that verifies its nature. So why do we verify the header, or we look at the header? Because we want to look for the signature. The signature verifies the nature of the file. If the file's extension is exe, after looking at the signature of the file, we can verify that it's indeed an executable file. Sometimes a file could be coming as, or the extension of the file could be PNG, and when looking, or upon looking at the signature, we see that it is executable. So it's very important to look at the header. And lastly, we can supplement the findings of the basic static analysis with online scanners, such as VirusTotal. Now, what are the basic static analysis tools? We have the PS3. This works for Windows. PEcheck, this is also for Windows, to analyze the portable executable header, the process doctor, and we have XXX hex editor to examine the hex, or to examine the file in hex view. And lastly, we have detected easy, which tells us whether the executable file or whether the binary is packed. Now, packing is a tactic malware analysts use to hide or obfuscate the code of the malware. So basically, we use detected easy to tell whether the executable was packed or not. Okay, now having concluded basic static analysis, now let's start with advanced static analysis and then on to dynamic analysis. So what do we look for when we do static or advanced static analysis? So basically, advanced static analysis is digging deep into the binary. In other words, you might call it reverse engineering. So what do we look for here? Again, we look for strings, we look for API calls. So API calls are a collection of functions and services that Windows operating system provides in order for developers to create applications. So basically, API calls are very necessary for applications and programs to work. So during static analysis or reverse engineering, we look to extract API calls, because extracting the API calls will definitely tell us what the malware does or what the binary does, as well as an insight on its behavior. The function calls, what are the functions that the malware or the binary calls, execution flow, and the DLLs and the exports. Basically, when you analyze the binary using disassembler or a debugger, we can basically extract all of these bits of data. Strings, API calls, function calls, all of these can be extracted using a good disassembler. What are some of the tools that can we use? We have Ghidra, which is the subject of this course. We have Radar 2. Radar 2 can work on Linux as well. IDEA Pro works on Windows, and only debug can be found on Linux and Windows. All of these can be considered as reverse engineering tools. They can be used to disassemble, decompile, and debug a binary. Now, what is the difference basically between a disassembler? I'm going just to write the abbreviation, disassembler, and we have decompiler. And lastly, we have a debugger. So what's the difference between these? A program can act as a disassembler, decompiler, and debugger at the same time. Ghidra is one of these programs. That's why we're going to use it throughout this course. So a disassembler is a program that converts the compiled binary into an assembly code, from compiled C into assembly. Oops. A decompiler is also a tool that decompile the compiled binary. Basically, it reveals the C code or the C++ code or the code itself. It could be written in another language. And lastly, the debugger allows us to extract errors and bugs in the program. Okay, so having now understand the methodology of advanced static analysis, let's now hop to a dynamic analysis. So in dynamic analysis, you know that the cornerstone of dynamic analysis is interacting with the file. So here we open the sample. Okay. Now that's very basic difference between dynamic analysis and static analysis. We open the sample and we interact with it. Before I hop to the methodology of dynamic analysis, let's talk about these. So these are common API calls that when we find them in a binary, when I find a binary, when I spot a binary performs these API calls, we pay a closer attention to it. These API calls mostly used by malware samples. Let's go over them one by one. So we have first one, get keyboard state, gets the status of the keyboard. This is used by keyloggers. Now, I'm not saying these API calls exclusively used by malwares. Of course not. These API calls are there or developed by Windows in order for developers to create applications that function. But these API calls can also be used by malwares to facilitate their objective or their working. So basically, another one is URL download to file and internet open URL. These two APIs interact with the internet and retrieve a file. They are used basically by droppers and downloaders. FTP put file uploads a file into an FTP server used basically by malwares that perform data exfiltration. Create process, also used by malwares, basically droppers. In order to install another malware, it needs to create a process for that new malware. Get process address and is debugger present. So get process address, we extract the memory location of an exported function. We talked earlier about exports and DLLs and why it's important to analyze them while during the advanced static analysis. Basically, when we look into exports and DLLs, we can see if this API call is used. If it is used, it means that the sample is trying to retrieve the memory address of one of the DLLs or exports. Why it might need to do that? Because it might want to hook or perform API hooking to that DLL. And lastly is debugger present. It verifies whether a process is running in a debugging mode. This is basically used by malwares that evade detection and VMs. Okay, now let's talk about dynamic analysis. So what do we look for when we open the malware and open the sample and interact with it? First, we look to examine the processes. When we open the sample, we need to find out what are the processes that are spawned when this sample is opened. Looking at the processes will enable us to find out what are the DLLs of this used by this process, what are the API calls used by this process, in addition to some other important information such as memory addresses and file locations. Network connections. We can verify whether the binary or the sample makes network connections. Opened created files. So here we see what are the files that are created as well as the directories that store these files. This is very important for droppers because droppers tend to download files from the internet and drop it in some other location. So here we examine the created files and the opened files as well. Registry keys modified and created. So some malwares modify existing registry keys such as the run once so that the malware starts when the system or when the user logs in. This is a mechanism to create persistence. And event logs. Although event logs are used normally for troubleshooting and performing blue team tasks, you can also use event logs to see the effects after running the malware. You can even find out the registry keys, the open created files, network connections, some of them, by just examining the event logs. Of course, to examine the event logs, we have to be familiar with the event codes because every event code represents a specific operation. All right, what are the tools to gather this information? We have Process Monitor, one of the most popular tools that works on Windows operating system. Event Viewer, to view the event logs. This is pre-installed on Windows. Netstat works on both Linux and Windows. And we have Wireshark, the popular packet analyzer. And also you can use CrowdStrike suite of tools to dynamically analyze the sample. All right, in the next section, we will look into the methodology of reverse engineering or advanced static analysis. We're going to use Ghidra and we will demonstrate the various sections that constitute the or this program, as well as we will look into different samples, analyze the assembly code, and see the various sections that can we look at in order to extract these pieces of information. Now it's time to go over one of the most popular disassemblers in the world of malware analysis and reverse engineering. Let's double click on Ghidra and explore the various features before we start analyzing a sample program. Okay, so from here we start a new project. We're gonna click on File and then New Project. From here, select non-shared project. Next, name your project. We're gonna name it as Hello World. And then we're gonna click on Finish. As you can see, the project has been created. We're gonna drag and drop the file or the sample we would like to analyze. So it's Hello World. We're gonna drag and drop here. Here we can check the basic options. The format is portable executable and other options seem fine. We're gonna click on OK. And now the program is being loaded into the disassembler. Okay, now we have this summary. Let's see here. So we're fine with that. We're going to click on OK. Okay, so now we're going to click on the tool chest. Click on this dragon that represents the code browser. And now we're asked whether if you want to analyze the sample. Of course, we would like to analyze the sample because this will fire all the add-ons and plugins that Ghidra is armed with. So when we trigger these plugins, Ghidra will analyze the file or the sample in a holistic fashion. So click on yes. And from here, it's giving us the option to select what plugins to load. So we're fine with the current headings. Click on analyze. Okay, so now let's go through the basic sections of Ghidra. So on the left here, or on the upper left, we have the program trees. This will list all of the basic sections of the code of the sample. So as with any portable executable sample, we have the headers, the text, the R data, and the other sections. You can find these sections typically in any portable executable. In some obfuscated samples, you might find these or the names of these sections not as we see now. So the important section we have here is the text section. Clicking on this will bring up the assembly code on the right. Even if you don't double click on the text section, the section on the in the middle here, it shows the assembly code. Okay, going back to the left pane, we have the simple tree. The simple tree shows all of the API calls and the functions the sample calls. For example, in the imports, we can see all of the API calls that the code performs. In addition to that, we can see the exports. In the exports, we can see all the API calls that the function or the program exports. And from here, we can see all the DLLs that it calls. We can see the code section that performs the call here. As you can see, it's highlighted in gray. Along with that, we can see the functions, and that's also a very important section to analyze because it contains the functions that are used in the code. Among these functions, we have the entry. Double clicking on the entry here, you can see local 8, local 14, and other functions because this entry function highlights the beginning of the program. As you can see here, we double click on that and we are in the same pane here because we are already in the beginning. Okay, and data file or data type manager, we can see various data types in the program, and on the middle here we can see the listing pane. The listing pane shows the assembly code. As you can see, guys, this is the assembly code. And if you have watched my previous video on assembly language, where I briefly explained all of the basic aspects you need to learn in order to start reading code in the assembly language, if you have watched that video, it's not going to be difficult for you to understand what's going on here. So as you can see, guys, we have various sections to go over here. So we start with the section on the left. These are the memory locations or the memory addresses of every instruction. And this is the opcode. Remember, the opcode represents the assembly instruction, right, but in computer language. And its assembler job here is to convert this opcode into a human readable instruction. So the opcode for call is this. This is an example. Here we can see the assembly instruction. In this case, it's call. Here it's pop. And on the right, we see the operand. The operand or the operands are the objects on which the function or which the instruction, the assembly instruction, is being executed on. Okay, now on the right. On the right, we can see a decompiler or a decompiler section. This is a section that shows the C code of the, the C code of the sample. You can see whenever we click on an instruction, the C code changes. So here, if I scroll down and I click on this, you can see corresponding C representation of this assembly section in the program. Okay, now we're gonna click back to entry, and into entry here we can see, guys, the start of the code. And indeed, the start of the code, we can see a function call. It is void. It's the entry function. And there is a call to another function named security initialize cookie. You can also see this function here, security initialize cookie. Double click on this, we are redirected to the function itself. On the left, we have the assembly representation of the security initialize code that we double clicked on, and on the right, we can see the decompiler or the C representation of this function. That's a basic overview. Now, one of the most important aspects of static malware analysis is to analyze strings. So to analyze strings, you can go to search, and from here you select strings. And here you define the criteria. Okay, so require null termination, and here the minimum length of the string. So click on search, or here the word model. Once you click on search, it brings up the strings. And from here you can start filtering. For example, let's say hello, and we can see the parts of the code that contain the word hello. That's for the strings. And one important aspect of Ghidra is the graph view. Now, to examine the graph view, which is another important feature in Ghidra, we have to go to functions, highlight the start of the code, entry, and then clicking on this icon, display function graph. As you can see, we see graph representation of the function, how it starts and how it moves through the various instructions. And from here also we can, in a graphic fashion, examine the control flow of the function, of the code. Okay, so now we're going to load up different samples where we can see different code logic and use of if, while, and for loops. For example, if we create a new project, and from here I'm going to open the tool chest, and then going to open the if-else program. Request to analyze, no problem with that. And as with every case, we're going to start looking for the main function. So on the left, clicking on functions, and from here we can see the M. So usually you can find the main function in three ways. You either locate the entry function, the start of the code, or you locate a folder or directory with the word M. So double clicking on that, we don't see the main function here. So rather we're going to double click on this, and from here we're going to locate another directory that starts with _M. Double click on main, and here we can see the main function. So this highlights the main function. Here the code with the main function, and here a printf or statement that prints something out of the screen. The program demonstrates an if-else statement. We have another call to the printf or puts the sum is equal to 500 value. So we click on the main function, and on the assembly code here we can see the representation of this in assembly. So here we can see the instruction call and the name of the function. Here it's an operand. On the left we can see the memory address of the instruction, and following along with the code we can see here the call to print the statement. This program demonstrates if-else statement. You can double click on the puts and takes you, wait, so clicking on the puts we can see the call to the puts instruction, and there is another put here. It shows the call to the put instruction, and we can see the actual value being printed to the screen. We can see it is done through the move instruction, and specified the word ptr will specify that we are printing a string, or the operand is a string. And here we can check the stack pointer that points to the corresponding variable. Same with this one. We can see the type of operand we're using when we want to use a string or to print out a string, right? So now let's take a look at the other program. From here we're going to open a project and click on the while loop. Same drill, locate the main function. So here we cannot find in this directory, this one. Let's see here, M, and we have the main function. Same thing here, we have a call to the main function, and then something is the statement this program demonstrates while loop is printed out, and we have a for loop here in the C code, or we can see the actual representation here, as you can see guys, with for the while loop. So here, look at this, jump if less than or equal instruction, and as you can see guys, in the C code here we can see the actual value is 5. So if the value of the counter, which happens to be local _14, is less than 5, less than or equal to 5, it's actually here only less than, so less than 5. So basically what happens here, let's go back to the C code. We have a variable code local _14 equals to 1. Okay, and the actual operation is presented by the assembly code. Here we have the instruction move that moves the value of 1 into the variable local _14, represented by this format. And then we have the condition here where local _14 should be less than 5. And then we have click on local _14 where it increments the value of the counter through the add instruction, as can be seen here. So 1 is being added to the value of the counter defined. And then we have here after so let's go back to the condition. So the condition here compares. Look at this one. So here we have the compare instruction that makes sure that the value of 1 is less than 5 through this comparison instruction. Remember that comparison subtracts the source from the destination. Here the source is 4 and the destination is the value of the local 14. Based on the comparison instruction, we know if the result is true or false, right? Remember that the comparison instruction result is stored in the flags. You either have a 0 flag or you either have a carry flag. So if it is less than 5, then everything is okay. It's gonna use the put, it's gonna print this out. It's fun to learn at THM. So what happens here is that the value of local underscore 14, as long as it's under 5, through this instruction, it's going to, let's go up, to move or to perform this move instruction, which print out it's fun to learn at THM. Now, what happens when the value of 1 or the value of local underscore 14 is equal to 5 or is more than 4? Let's say it's more than 4, because the condition here, the for loop will continue working as long as the local underscore 14, the variable or the counter, is less than 5. So when the for loop breaks, we know that the local underscore 14 or the value of this counter is now more than 4, right? Because more than 4 meaning equals to 5 or greater than 5. So if we scroll down again, what controls that is this comparison here. This comparison is controlled by this jump less than. So we have this going up to this section. This section is the actual core or the core of the for loop, where the statement it's fun to learn THM is printed and an increment is made to the variable counter. So as long as the variable counter is less than 5, it's going to perform this jump. It's going to go back here where it's going to print it's fun to learn THM and it's going to increment. Now, as a result of the what's happened? Okay, as a result of the increments to the local underscore 14, it's going to come to a point where this variable is more than 4. So the result of this comparison is not 0. So when it comes to this, it's not going to perform the jump because the result of this comparison is not 0. When the result of the compare is not 0, it's not going to perform any condition comes after it. So it's going to execute this instruction move where it's going to print this out. That's the end of the while loop. Okay, going back to the questions and answers. What value gets printed by the while loop in the while loop program? It's fun to learn THM. Actually, if you have carefully watched the walkthrough, you'll be able to answer these questions without me going through over them. How many times the while loop will run until the condition is met? It's 4, less than 5. Examine the while loop. I'm going to answer this. What's the virtual address of the instruction that calls to print out the sentence at the end of the while loop? So we're going to click on the function that calls this or to prints the statement, and we can see the address, the memory location. It's found on the left. Now, same with this one, and this one is also easy. The most popular techniques used by malware developers is process hollowing. So in process hollowing, malware developers create a malware that is designed to evade detections and avoid being caught by AV solutions. So how a malware employs process hollowing. So basically the malware goes through several steps. Once the malware lands into your system, so here is the malware. Okay, now the malware is in your system. Once the malware lands there, and before it executes, what's going to do, it's going to analyze the environment. After the execution, it's going to analyze the environment, and if it is designed to run process hollowing, it's going to go through several steps. Let's assume for now that the malware will create a process called Chrome with EE, indicating a typo in the process name. Because originally, if there was a original process named Chrome, the malware cannot create the exact same name. It has to be some other name. So in order to evade detection, the malware will create a process with a similar name. So it could be Chrome with EE at the end. So first step is create a process in a suspended state. The malware will create this process but will not run it. And how it's going to do that? It's going to do that through 2 API calls. The first one is create process, and the other one is suspend the process. So these 2 API calls are connected. So once the malware creates the process, it's going to suspend the process as a first step. The next step is to allocate the needed memory. Going to request memory from the OS for this process. Since this process is meaningless, it doesn't do anything, the OS will say, all right, yes, I'm going to allocate memory for this process. There is nothing wrong with this. So the next step is allocate memory, which is basically preparing storage for the malicious code, right? Because the malware contains malicious code, a storage will be prepared for that purpose, and of course it's going to be done through the API call virtual allocation. The third step here is writing the malicious code. Now, after the storage has been prepared, the malware is ready to load its shellcode into the allocated memory. So here, the memory now is filled with the malicious code. Pay attention that this is all happening in memory. Nothing is written onto the disk. That's why it's a very effective method to evade detections. Most AV solutions rely on scanning the disk to detect malicious code. However, in process hollowing, everything happening here is taking place in memory. Okay, so memory now is filled with malicious code, but through what? Of course, we're going to need an API call. The API call is write process memory. So why are we mentioning the names of the API calls? Because later on, as we're going to see, when we analyze a sample that employs process hollowing, you'll see that it's very important to be familiar with these API calls as they are being used by samples employing process hollowing. That's why we're trying to get ourselves familiar with these API calls. Once we spot them, we know it's time to take a closer look at these API calls. Now, after the malicious code is loaded into memory, it's time now to set the entry point to run the malicious code or to run the shell code. Remember that the process here is just a meaningless process. It does nothing. So in order to run the shell code, we need to set the entry of the entry in memory to run the shell code. The shell code has to be run first. So we set the entry point to the shell code. Starting point is the shell code. We do that through two API calls, set thread context and get thread context. Next, after we have prepared the process, the storage or the memory, and the entry point, now it's time to resume the suspended process. Remember that Chrome is in a suspension state. In order to run the malicious code, we're going to have to resume its operations. That's why we need now to resume the suspended process. So here we are running the process, and we do that through net resume process. Now the process is running smoothly with no issues. It's going to run. The AVs will be clueless on what's happening. Now, yeah, the malware could be detected later on through heuristic monitoring and through observation of the changes done on the file system, but it depends on the security measures installed on the OS, right, or in the network. Now, after everything is finished, the malware will unmap the memory. Which memory? The memory it has allocated in the second step. It's going to unmap the memory, performs a cleanup through these two API calls. Next step now, we're going to take a sample that employs process hollowing and see how this all happens behind the curtains. Now we have a sample which employs process hollowing. So what's the first step when analyzing these kind of samples is to analyze the imports, the API calls. Now in analyzing API calls, we would like first to take a closer look or a general look at the imports. So under kernel, we have create file, create process, get file size. Let's see here, we have virtual allocate. We explained most of these API calls, so I'm not going to repeat them again. So under kernel, we know what there is no user called API calls. After the imports, you can see the exports. So it's only the entry here. And under functions, we can take a look at the functions. This is the start of the code. It's very important to start the analysis from the entry, the start of the code. If you want to take a look at the main function, you can look for the main function here. It's somewhere main. We can just look into main from here. There is no main. Okay, in that case, we can start with the entry. Okay, since we are interested in analyzing whether the sample employs process hollowing, we're going to examine the API calls because API calls determine the behavior and capabilities of a sample. So in the import section, you can see the API calls. So how to start? Since we are looking if the malware employs process hollowing, we're going to need to go back to what we have explained earlier. These are the API calls mostly witnessed, used by malwares that employ process hollowing. So the first one is create process, which is fine. It's very necessary for a sample to create a process in order for it to function. But we want to see what kind of process the malware employs. So we're going to go back and look for create. So create, we have two API calls that start with create file A and create process A. So right click on the create process A and click show to references. Here we will see how many times the API call was I'm going to say summoned. So basically here we can see only one call, and when you click on the call you can see the relative section in assembly and in C. If you click on the other one, again you are redirected to the relevant section in assembly and C. Let's take a look at the first one. So here we have a call to the create process A, and we can see the corresponding section in the C code here. So this is create file. I want to create process. Here it's highlighted in yellow, and we have a create process API call. As you can see, it takes a couple arguments. Among them is the process that's going to be created. This is the name of the process that is created. So far, so forth, it's okay. Now, we know that in process following, we have created process in a suspended state. Let's see if this API call is called. So we're going to look for NT suspend. Let's see here. If you couldn't find it here, you can follow through the code here. So after the API call is performed by creating the process, you can see here there is a condition based on which we have two outcomes. The first one is failed to create a victim process. If the process was not created, we have this code block executed. If the process was created, we have another code block that is executed, which prints out created victim process. And we have the PID information printed out, and then we have another API call. And then we have terminate process. So here where it terminates the process or suspend it. So in this case, it did not use NT suspend, it used terminate process. Before we continue further, let's take a look at the create file API call. So create a file API call creates a file. So let's take a look at the file. So this file, somehow it has a purpose to serve, and we're going to learn that later on. As you can see, this is the file it's going to be created, and then we can see another if else block. So if the condition, look at this, get last error, a function unable to open replacement executable, terminate process, or if the condition succeeds, it's going to execute this code block where we can see the replacement executable opened, its size is calculated using virtual allocate. Remember, virtual allocate is used here. Why it's used? To allocate the memory. So here, this executable will be loaded in memory. So that's actually, or in fact, the executable that contains the malicious code. It's not opened, it is just there lurking in the shadow. Virtual allocate is going to allocate the size, right, of the shellcode calculated by this line. And after the size is calculated, it's going again to go through an if-else block. If it failed to perform that calculation, it's going to say unable to read replacement executable into an image in memory. If it was successful, it's going to say, all right, read replacement executable into memory, and then we get thread context. So get thread context, it's an API call that we also talked about here. Get thread context, it sets the malicious code at the start of the, or at the entry of the process. This is where it's preparing the shellcode to fire. And then we have read process memory. Let's scroll down. NT unmap view section. So remember, we talked also about this. This is a stage where it performs the cleanup. And then we have an if-else statement. Okay, and here as you can see, hollowed out victim executable. After it allocates the required memory and loads the shellcode, it performs the hollowing to unmap the target memory, or to unmap the memory from the target process. Okay, an alternative method to follow through the execution path is to use what is called as the graph view. So click on the graph view here, and we can start from the very beginning. This is the beginning, and here we can see the first API call. Look at this. If you can locate any section from the graph view by clicking on the section, and here we can see it is highlighted in the C code, right, and in the assembly. Going back here, it goes through the same logic. So the execution flow here, after the API call is performed, create process, we have two execution paths. The first one indicates a failure in creating the process, and with the green arrow we have success in creating the process. Look at this. This is what judges the comparison process. It tests the values pushed into the EX register, and it jumps to the section highlighted here, lab_0040102. So whether if the condition was successful, it's going to perform GNZ. So not zero flag. If the zero flag was not set in this comparison, it's going to jump to this section. In this section, it's going to call the next API call. So it's going to go through all of these API calls based on an if-else statement, as you can see here, all the time. Okay, so that is a brief analysis of a sample that performs process hollowing. Most important is to understand the methodology all the time. Start with functions and locate the entry or the main function. If you have something in mind, you can look through the imports or the exports if it is a DLL, or you can use the strings. And make sure to utilize the graph view because it's very easier to follow the execution flow through this feature. Okay, in TryHackMe there is a room named Advanced Static Analysis, and this room is marked under the SOC Level 2 Malware Analysis track. If you've been following carefully the explanation, you will be able to easily solve all these questions. Nevertheless, let me go over the answers quickly. So, does advanced static analysis require executing the malware in a controlled environment? Nope, because it doesn't open the file. Okay, how many files are present in the C constructs folder on the desktop? And once you open the machine, you'll be able to, I'm just going to hit here, you'll be able to find the number of files. There are 5. Okay, now on to Ghidra. How many function calls are present in the exports? What is the only API call found in the user? How many times can the hello world string be found? And what is the virtual address of the call function? All of these questions can also be answered easily if you have been following carefully the walkthrough on Ghidra. Task 5, but nevertheless, these are also the answers. Task 5, we have what value gets printed by the while loop in the while loop program? How many times? Again, all the questions can also be answered in the same fashion. Task 6, when a process is created in a suspended state, which hexadecimal value is assigned to the creation flags parameter? It is 4 in hexadecimal because that's how it is documented in Microsoft documentations about API calls. Task 7, no answers are needed. Task 8, which API is used to write malicious code to the allocated memory during process hollowing? We also talked about process hollowing. It is write process memory. Remember this one, where we prepare the memory to be filled with the malicious code. Task 9. Task 9 is a bit long. Let's see here. What is the MD5 hash of the P9 sample? Okay, this one I think we're gonna have to take a look at. So let's reload the sample. Let's reopen the machine. Anyway, next question. How many API calls are returned if we search for the term create? This also requires us to open the sample. But anyway, we have done similar work in the previous sections. What is the first virtual address where the create process A function is called? Simply once you locate the API call, you click on right-click, create, or select show references. You'll be able to find the virtual address, which process is being created in a suspended state. By the way, these answers, yeah, I remember now. These answers can also be found in the walkthrough of a previous section, because actually the malware we have analyzed is taken directly from this section, from this task, but I forgot to mention. Anyway, that is for this room. Let's see other things we have to do, other rooms. Let's terminate for this for now, no need. Go to malware analysis. So far so forth, we have finished everything. We still have to go through maldoc, static analysis, anti-reverse engineering. Alright, so that is for the next videos.